Action, and we're live. All right. Now we're going to create a science notebook page to record what we've been learning about orbits. Not the travel company or the bubble gum, but instead, when we think about gravity and the solar system, we're going to learn about orbits. So let's look at the science notebook page, how it needs to be set up. You need to make sure you have the heading at the top of the page. And then we're going to do a demonstration and kind of a thought experiment about if we were to fire a cannon, followed by a definition of orbits, or of an orbit. And then we're going to look at another thought experiment about a person falling in an elevator, and we'll record some notes as we go along. Finally, we will come up with some conclusions that point to the fact that there is no such thing as zero G. So let's dive in. All right, so a famous thought experiment conducted by, I believe it was Albert Einstein. He considered if we had a giant cannon that was on the Earth, and if we were to shoot that cannonball with a certain amount of force, that cannonball would travel forward until it lost its momentum from the amount of force that was applied, and it would then plummet down to the ground. Just like as we throw a ball on the surface, we throw it and it travels forward for a certain distance, and then it eventually falls down to the Earth because the Earth is constantly pulling it towards the core due to the Earth's gravity. So, since it has that downward force towards the core of the Earth, we can apply more force, but it's still going to just end up falling to the Earth. If we apply even more force, it's going to travel until it loses that momentum and gravity overpowers it, and it then falls to the Earth. And again, it can continue going, but it'll fall into the Earth until there's a magic amount of energy. And it's not magical at all. It's actually something that can be calculated, where it no longer actually hits the Earth's surface, but it then continues around the Earth again and again and again and again because it has enough forward velocity. So if we looked at like a free body diagram of this object, it's got gravity pulling it down. And so that's why most of these all fall to the Earth. But at some point, once the amount of force forward overpowers the gravity, then it's going to have this type of path here, which is going to then, it's going to allow it then to continue to orbit around the Earth as that cannonball just did. All right, so if we were to define an orbit then, an orbit is a curved path of an object affected by the gravitational field of another object. But that other object has to be bigger, or we could say actually a more accurate way to say it is it should be more massive. So if we're talking about a cannonball and the Earth, then it can orbit. And that's how we put like satellites into space. As long as it has enough forward velocity and it's close enough to the Earth will pull it, but it's moving forward, so it actually ends up orbiting. So it's that curved path of an object affected by the gravitational field of another object. So if we look at these massive objects right here, let's think that the white dot is like the sun in our solar system. The little dashed lines show a top-down view of what the gravity field would be like. And so let's see. Let's have an asteroid coming in hot here. So actually, let's look at this. If there was an object that appeared like it was going to come really, really close to the Earth, to the sun, but it wasn't going to actually hit the sun. It was just going to get really, really close. It would come in here, and if it wasn't going to hit it, but it got close, it would get wrapped up by these gravity fields. It would be pulled by the sun's gravity as it went around, and it would get so much extra. It would be pulled in, but it would end up having all of that extra like momentum from turning that corner that if it had too much velocity, it would actually just get shot back out in the opposite direction. And this is actually what NASA uses this tactic right here in order to send different spacecrafts far out into our beyond our solar system. They do this. This is called the gravity assist, where they get really close and they use the gravity of the planet or the moon to actually then shoot the object in a new direction, or to just actually cause it to speed up right here. So you can imagine if you were spinning on ice skates and you were holding on to someone's hand, and then if you spin faster and faster, if you let them go, they would fly outward. And that's what's happening here, is this thing is flying outward because it gets this extra little spin. Now something was going to be coming in, and we have another object coming closer to our sun, but maybe it's not moving, it's not going to come exactly to the middle of this area. It's going to be more in this outer region. What we would see is that it would be pulled in towards the sun, and it would still continue to pull it. The amount of pull, though, would decrease, and so maybe that object actually ends up having some type of arc. And lastly, let's imagine if it was even further out in this trajectory, in this path, and it was going to be in the outer realms of this field of gravity. You can see that, the amount of gravity would be less, as we learned in our gravity page. So it might just be altered just by a little bit. But regardless, gravity is going to affect things depending on how close it comes, because gravity increases as you get closer to that mass, and the force of gravity decreases as you get further from the mass. That's what we learned in our gravity page. So you can now see how orbits can actually be different depending on the mass of the object, the gravity fields, and the distance at which it interacts. So then Einstein was looking out a window and he's like, what would happen if we had an elevator? Well, if an elevator was just simply falling, let me get back to my right color here. If it was falling down, it would be falling at the rate of gravity, which is g, or 9.81 meters per second squared. Okay, so this could fall forever in a theoretical situation, but let's think it would just be falling, and it would just continually fall. And if a human were to fall, well, this human could be in that elevator, and they could also continually fall, and they would fall, and gravity would be pulling them at the same exact rate. So they would be falling also at 9.81 meters per second squared. Well, then Einstein was thinking, well, what if that person was in the elevator? Woohoo, yay, I'm in the elevator. Probably pretty scared, but falling at the same rate that the elevator is, hoping that the ground isn't coming near. But let's imagine there is no floor. Well, if both were falling at the exact same rate of 9.81 meters per second squared, well, the person falling at the same rate as the elevator, so the person in the elevator are falling at the exact same rate. That rate is 9.81 meters per second squared. It would appear that they would be floating, because they would be falling with one another. And so actually, if you want to see an example of this to prove this point specifically, you can watch any of the International Space Station videos on the SciFlix, or the skydiving video that's also on SciFlix, because this will show that when things are falling at the same rate, it appears as though they're floating, and it appears that there is actually zero gravity. But as you watch those videos before in your YouTube binge assignment, you'll know that they're really just, the gravity's still affecting them. It just appears that they're floating. They're not actually in a zero gravity environment. And so the reason that this is happening is because if you see that we have this structure here is our International Space Station. And as the International Space Station, it's orbiting our Earth. And the reason it orbits our Earth is because it is falling constantly. It's falling downward, but it's falling down, but it has the forward velocity of its motion, and so it's actually moving at a diagonal path until it gets to this position here, and then again it's going to fall downward, but gravity is going to pull on it. So as it falls downward, gravity is going to continue to keep it close, and so it just ends up creating this path around the Earth. But essentially, it's constantly falling because there is no up or down or right way. So really, when you're looking at outer space, you can't say left or right or east or west. Really, this thing is just constantly falling. But it ends up orbiting the Earth because the Earth is more massive and the Earth is pulling on it as it moves forward. As it moves forward, gravity's pulling down on it, so it ends up going at this orbital path around our Earth. So you can imagine then, as this International Space Station is falling towards the Earth and there are people in it, it looks like the people on the ISS are truly floating. So it appears as though they're floating, but anyway, if we look at like on the International Space Station, this structure right here, it appears that there's zero gravity, that they're floating, but there is no such thing. There's no such thing as zero gravity. Oh my gosh. It just depends on the observer, where you are, and the reference frame that the person is in. And that's why OK Go could make their music video. That's why the people on the International Space Station look like they're floating and that they have 0G. But really, there's no such thing as 0G. So now you know it. Go tell your friends, and I'll see you on the next vid. Peace.